In this video, we're going to show you how to use Gauss's law for a symmetrical charge distribution to solve for the electric field. Now, in order to do this, we're going to have to know the way or the pattern of the electric field lines of the charge distribution. Alright, so if you can't draw the pattern for the electric field lines, that means you don't understand the problem well enough to use the symmetry in Gauss's law to solve for the electric field, and you'll have to use some other method. But assuming that you can draw the electric field lines from the system, then you can apply Gauss's law. So, as a particular problem example that I'm going to use as I go through these steps, we're going to start with a charge of Q here. And the electric field lines for this Q, I know, flow outwards. So by symmetry, I know these electric field lines flow out like this. I'll just draw a few of them so that I can have some things. So they have a symmetrical spherical symmetry. They have the same shape as the charge. So I know basically the shape of the field lines. And I know if it's a positive Q that the field lines are all going out. And if the Q is a negative, they're all coming in. So that meets the first part of the thing. Number two, choose an appropriate Gaussian surface. It should be chosen so the electric field lines are either perpendicular with the same strength or are parallel to the surface at every point. It must also have the point where you want to calculate the electric field strength. So let's say that I wanted to calculate the electric field at some point, let's say at a distance r, right here, some distance r, that's where I want the electric. Then my surface has to include this point. I need to find a surface that's perpendicular. Well, that's easy. It's a surface right like that. That's perpendicular. It needs to be perpendicular to all the lines as I go around. So if I do that, what I need to draw, at least as best I can, is a sphere. Forgive me of my lack of drawing skills. A sphere of radius r. That's my Gaussian surface. And I'm going to want to know the electric field at each point along that surface. But by symmetry, if these lines are going out and spreading out equally, then the electric field that's related to the density should be the same at each point on this surface. The electric field is a constant. Now, if I did not know that, then I couldn't use Gauss's law. If I had drawn some other shape, say some rectangle here, then the electric field would be having varying angles because the surface area's angle would be straight up for its area, and these would be a different direction. But the sphere, it's at right angles at each point. So I'm going to be looking at cosines of 0 degrees because my area vector points in the same direction for my Gaussian surface as my green electric field lines. So these are the first two things I need to do. Find a Gaussian surface that fits these requirements. It's a general rule. For cylindrical objects, use cylindrical surfaces. For spherical objects, use spherical surfaces. And if you're looking for a plate, as in a parallel plate capacitor, in the next chapter, we'll use plane surfaces. Make the surface the same as the shape of the object you're trying to solve. Find the area where the electric field is perpendicular surface. Okay? In our case, the area is 4 pi r squared. For our sphere, it's going to be 4 pi r squared, where r is the radius of our sphere for our Gaussian surface. Find the net charge enclosed by the Gaussian surface, and solve Gauss's law to find the electric field strength. Finally, use symmetry to get the direction. Now, what do I mean by this? If you can find a surface of symmetry, you can rewrite Gauss's law as follows. The cosine of theta is going to be 1. Remember, Gauss's law says that our closed flux was EA, cosine of this theta, as we did it over all of the surface. If these guys all happen to be such that they're 0 degrees, then this cosine has become 1. If this electric field is constant, it can be pulled outside. And it doesn't need a subscript because it's a constant. So now, all I have in here is the sum of areas. Well, that's just the total area. And we know this is all equal to Q enclosed over E naught. So I can solve by E if I just divide this by A. And so I've written Gauss's law in a way that you actually work problems. The electric field is 1 over epsilon naught times the enclosed charge divided by the area of the Gaussian surface through which the flux flows. And if you prefer, you can of course multiply the top by 4 pi and the bottom by 4 pi and write this as E is 4 pi K Q enclosed over A. So let's put that to work in our problem that we have. So I've drawn my surface. There's my field lines. I want to find the electric field. It's going to be equal to the Q enclosed. Well, the only enclosed charge in my problem is this Q here. There's nothing out here. Just this Q right there, which I was told had a total charge of big Q. So I've enclosed all the charge. My answer is big Q over E naught times A. That's Q over E naught. My A is 4 pi times the radius of my sphere, which is r squared. So my electric field is, now let's see, 4 pi epsilon naught. Well, 1 over 4 pi epsilon naught, that's K. So KQ over r squared. And it points outward in the radial direction according to my field lines. So the answer to the point, assuming that I'm outside the sphere, so I've enclosed all the charge, is just KQ over r squared r hat. This is just the formula that we had for the point charge, which you should already know. Now let's now assume that we're going to be inside the charge. If we're inside the charge in here, and so this is our R, and it's less than big R, then we're only going to enclose a fraction of the total Q. So we do exactly the same thing, but when we calculate the Q on top here, it's not all the Q, it's the fraction of the Q that's inside. Only the enclosed charge, not any of this white Q, counts. So for inside the sphere, we again have the same formula work. E is equal to Q enclosed over E naught A. The enclosed charge would be equal to the charge density that's charge per volume times the volume. Okay, now let's see. The volume is the volume of a sphere, 4/3 pi little r cubed. It's the volume of the purple sphere here. This volume is the enclosed volume, not the total volume. Assuming that rho was constant, equal total charge over total volume. So we could compute it for any volume, but I happen to know if you take the whole thing, then it's 4/3 pi big R cubed on the bottom, but I know the total charge big Q. I also know the area of my Gaussian surface. It's 4 pi R squared. So I know the area of the Gaussian surface, I know the volume of that surface, and I can calculate the density by taking the total charge over the total volume. So I know this. I can plug everything into the formula now and find the answer for my electric field. So let's see what happens, because we get a really interesting result. The electric field is equal to Q over 4/3 pi big R cubed, that's the total charge, times the volume, 4/3 pi R little cubed, and all of that is by epsilon naught 4 pi R squared. Now, some things cancel here. The 4/3 pi cancels the 4/3 pi there. This R cubed cancels this R squared. So we get Q. We have an R cubed here on the bottom and a 4 pi epsilon naught. Well, the 4 pi epsilon naught, that's K. R cubed. And then I have an R. So let me pull that up just a little bit. So my electric field is KQ over big R cubed, R, and it points outward. Now, key thing, that there is constant. So the electric field goes linear inside, whereas it goes as 1 over R squared once we get out. Let's graph that. Let's graph R and the electric field strength. And what do we see? Inside a uniformly charged sphere, it goes up linearly. And it does that until you get to the radius of the charge. And when you do that, you'll get a formula, KQ over R squared. Now notice that if you put big R in for little r here, it cancels, you get 1 over R squared. And you get that no matter which formula you use. Once you get outside the sphere, it falls off as 1 over R squared. It turns out forces of any type that are uniform obey this. This is because the volume goes up faster in surface area by R, and so it goes linearly up, and then the outside touches the sphere goes 1 over R squared. All right, we'll see you in another video.